Yep, thank you. So yeah, we'll do some generalizations of Motivic invariants in a setting where we have a fibration over the base, and we want to respect that fibration in some sense. But before that, I want to clear up some confusions regarding this various notions of rationality and ruledness that I was using, and maybe it's good to see them like once on a single board. So I'll compare various notions of rationality and ruledness which were appearing yesterday and which will keep appearing. So I have a variety x over k, and kind of there are maybe like five standard ways to measure how far it is from a projective space, right? So like in terms of rationality. So, and there are some relations between them. The first is the most kind of standard one. We say x is rational if it's birational to projective space. Yeah, so that's a rational variety. You have a birational map to or from projective space. So then you can compare it with x is ruled. So I guess you know ruled surfaces, and we can ask for the same thing, that your variety is birational to a product of P1 with some other variety Z. Yeah, so there's a ruling, birational ruling. I guess it's standard to say this for surfaces, and higher dimension we can just use the same thing. So, and of course we have this formally, and of course the converse doesn't hold. Take elliptic curve here. Okay, then we can weaken this and say x is unirational. And unirational is a classical notion. It means that there's now just a rational dominant map from Pn. Usually my dashed arrows are birationals, so this is a rational dominant map. So generically finite covering. You can even make this even weaker. You can ask for higher dimensional projective space dominating your thing, but then you can take hyperplane sections and you go down to dimension of x. This is an implication, and cubic threefold mentioned yesterday is an example of the other implication failing. It was unirational but not rational. So a strict implication. Similarly here we can weaken this to uniruled. The uniruled is a standard thing in MMP. It means, okay, but we literally do this kind of weakening. So P1 times Z dominating X, so rational dominant. Another way to say this is that X is covered by rational curves. So if you have such a map, then here is you're covering by rational curves. And conversely, if you're covered by rational curves, you can write a family of them. And then you can, you can also make this base to be n-1 dimensional. What do I need to ask? Yeah, that's the, yeah. But I think as we discussed yesterday, you can cut down the dimension to this if it's higher. Yes. Right. Okay, yeah, I want these curves not to be contracted by the map. Yeah, thanks. Thank you. Yeah. Okay, so then this is obviously holding like this, and the converse also fails. Right, and then there's like a fifth notion I want to mention, is rationally connected. So let's put it here. Also a very standard notion. So this means that if you take general points on your X, they can be connected by a chain of rational curves. That's the one way to state this. Yes. Yeah, it's a bit more natural to talk about this over algebraically closed field, actually, especially for this notion. So, okay, what are the implications? If you're unirational, then you can connect your points by curves coming from here. Right, this is clear. And also, if you're rationally connected, you can single out a P1 kind of family of curves and do this. So uniruled means it's covered by rational curves, and rationally connected means they go in all directions, these rational curves. Okay, so out of all these implications, the converse fails, apart from one we don't know, and this one is the interesting one. So one of the biggest kind of open questions in this rationality field is whether this is true. And no one believes this, so because this is about curves, and this is about like global geometry, and so there are these questions, maybe you have a lot of rational curves, but no rational surfaces or something, but there's no single counterexample to this statement, because it's hard to disprove unirationality, right? So that's like some kind of very old and important open question in this field. One needs some kind of conic bundle example or some kind of example which is provably not unirational. So yes, so this is kind of relevant for today because we'll be looking at MRC fibrations. So if your variety is not rationally connected, you can separate it into rationally connected direction and the complementary direction. So there's something called MRC fibration. MRC means maximally rationally connected. So constructed by Campana and Kolar Miyokomori. It tells you that if you have any variety, you can find a rational dominant map with a property, as I'm saying. So, namely, general fibers are rationally connected, and the base is the opposite, namely, not uniruled, not covered by rational curves, right? So the picture is rational curves live in the fibers of this map, and the base may contain some rational curves, but it's not covered by rational curves. Yeah? So some kind of conic bundle over an elliptic curve or over a abelian surface is doing that. Yeah, and it's so it's a very useful thing. It allows you to treat non-uniruled varieties separately from rationally connected varieties. It's a kind of easy sort of MMP claim. And furthermore, it's functorial. So if you have two such varieties, and you have a birational map, then you get an induced diagram. So basically, because this target won't be covered by rational curves, all the rational curves must map into the fibers of this map. So for every such map induces one on the base. So it's kind of functorial. And this kind of leads us to this question of horizontal and vertical invariants. So in settings like this, we'd like to separate the contributions to the invariants. So the goal for now is, given such a diagram, not necessarily coming from MRC fibration, but now just giving arbitrary such a diagram where these are birational maps, and I write them as phi and sigma, and these are dominant rational maps. We can look at this birational map from X to X prime, think of its Motivic invariants, but furthermore, I want to separate them into the ones which are horizontal and the ones which are vertical. So I want to write P of phi as a sum of vertical contribution plus the horizontal contribution. And I'll explain how to do that and how it's useful. So one way it will be useful specifically is to deal with this MRC fibration for threefolds. So that's like one of the examples for such situations. So yeah, just to emphasize, indeed, kind of the category where we live. So like in that situation, we kind of think as phi sigma lives in birational maps from pi to pi prime, right? So previously we had birational maps from X to Y. Now I have two such rational dominant maps, and that's the definition of a map from pi to pi prime. So it's a square commutative diagram with rational maps. So it's not super standard, but that's a very natural thing to do. And in particular, when pi equals pi prime, we can look at birational automorphisms of pi, which are birational maps from pi to pi. So the square diagrams, and very importantly, it's not the same thing as birational maps of X over B. So I explain the difference. So we have a certain subgroup here, and this typical representation means that we are acting trivially on B, right? So the natural setting is to have birational maps which twist the base, but sometimes we have those which act trivially on the base, where the squares collapse to a triangle, and this is typically noted X over B. So for me, those are not over B, but kind of preserving B. Yeah? And somehow it's very important sometimes to distinguish this. So basically, maybe the idea is to do some kind of induction on, so sort of what we'd like to do is we'd like to pass to the generic point of this base as downstairs and do some kind of induction on dimension. And this is what they're useful for, and this is how I introduce this horizontal and vertical invariance. So basically first, I'll introduce some auxiliary category which will help me work with this. To introduce something we call beer tilde over K. So previously we had this beer over K, which was just birational types. So varieties and birational maps. Now I want to do something which would look a bit like that. Okay, you'll see. So, okay, it's a kind of homemade notation, not a standard thing. So let me give you objects and morphisms for this category. So objects are varieties over a different field F, right? So we have a base field K, but now I want like a bigger field F. So it's an extension of K, so finitely generated extension. And X is a variety over this field. Kind of I have X over F over K. And morphisms are, if you have two such guys, this lives over F, and then it lives over K, and another one over f prime, and this lives over the same k. Yeah, so this is my one object, and it's another object. And what I want is I want a birational map here, which twists this base. Right, so importantly, I don't insist it's an identity, and furthermore, it cannot be identity if they're just different fields. It's just some kind of automorphism of this field. So we'll be doing a little bit of kind of Galois theory here. And I still write phi here and sigma here. So that's some kind of version of that diagram if I look at the generic points. Yeah, so that's a natural category to live in between just birational types over K and that actual situation I want to deal with. So I first want to consider this. So varieties over the field, which is bigger, and then birational maps twisting this field. So in this case, we can still look at exceptional divisors for find phi inverse and keep track of them as before. So slight generalization of what we had before. We can look at, for such a map, we can still define its Motivic invariant C of phi just by doing the same thing, by looking at exceptional divisors here and here. I want to write the same formula, so E is exceptional for phi inverse, device is created by phi minus D exceptional for phi. Now the problem with this formula is we need, like, they live in different places. So specifically, these guys live over this field, and these guys live over this field. So I need to make a choice where I want to consider them, and I put sigma here. Right, so this way I send everything to here, and I now can compare them. So this lives in the Burnside group of the second field. So I could have chosen this first, but okay, choose the second field to compare them in. Another way to think about this is, okay, you say that you have a variety over this field, but if you look at this kind of composition here, you get a variety over this field. It's not the same variety. It's isomorphic scheme, a kind of slight complication here. But then you literally do what we did before by looking at exceptional divisors this way minus exceptional divisors this way considered over this field. So you get this formula. So as before, n is dimension of x over f. So a bit later so far this field k is not used, but a bit later we push down everything to k and consider values here. This will be for the horizontal and vertical applications. So what's the additivity property? It's almost the same as it was, apart from there's a little bit of twisting going on. So we have, yeah, sometimes instead of the spec f, I'll just write f here. So this will means, okay, variety over a field f, and this is phi, this is psi, this is sigma, this is tau, and the claim is additivity property will be almost as it was before when all these fields were the same, but we have to twist something a little bit. So we have to do C of phi plus C of psi as before, and C of psi will land in this field, and C of the composition will land in this field, but C of phi lands in this field, so I apply tau here. Yeah. So I sort of say, okay, they're different fields, but let's consider them all over this field, and this is what we get then. Yes. So this is kind of, yeah, the base field changes here. And this is part of the object I start with. So that's my object. Yeah, so so it lives over this field. Yeah, it's a little bit now from a groupoid to groupoid. One can do it a bit differently. One can choose some kind of marking for these fields and choose another field isomorphic to all these. Yeah, that's right. So, yeah, okay, good point. I see the question now. Right. So, this was defined in the final field, and indeed, when we start changing these inputs, this field will change a little bit, and we keep track of it like this. Yeah, so this follows basically from what we had before if we consider them all over this field. Yeah, so now I want to push these invariants down to the same field, and then they'll be like, then it will be clear. It will be here in a moment. So for that, I'll need to think of the restriction. So there's a coefficient restriction homomorphism. You can look at birational types over big field versus birational type over small field. I said K is finitely generated, so it has a finite transcendence degree. And basically what's happening here is, so this was the free abelian group on birational types over F. In other words, this was classes of, so the elements here can be thought of function fields as a field extension of F, as an F field. And you map it into the same thing as a K field. So restriction of scalars. Right? You had this field over this field and this field over this field. And like, what's a variety? Birationally, it's just a finitely generated field extension. So literally, if we want to do kind of algebraic side of this, we just talk about finitely generated field extensions and their isomorphism classes. And then we can sort of forget that our variety was hanging over this bigger field and look at its function field over the smaller field. And that's not quite a variety, but it's a function field of a variety, which is a birational type. So it's well defined, and this plus m is the transcendence degree of, right, so basically if dimension of x over f was n, it means that transcendence degree of f of x over f is n, and then transcendence degree of f of x over k is n plus m. Yeah, so they become bigger dimensional kind. Geometrically, you can think, okay, maybe it was a fibration over this, and then you have to add up dimensions of these fibrations. And we'll do sort of these things soon. But let's see, yes, let's go into that. So, so it's still a field, right? So it's a finitely generated field extension of the base field is still a birational type. And so they can be inseparable, that's right. Yes, yeah, I don't care. I don't make field extensions. Yeah, I understand that if I start passing to k bar, if things were not perfect, I would have some kind of problems here. But as fields, I think it all makes sense. Thank you. Yeah, so basically now I want to put this situation together with this restriction and define horizontal invariants in that setting of square birational maps. Yeah, so the point kind of I'm making is if we want to do this, it's unavoidable that we have to twist the base field, because that's kind of what the diagram is saying here. Okay, so let's make this precise. Okay, so I first consider a slightly more special situation. I consider regular projections here and birational maps between them. So this is phi, this is sigma. Yeah, and I put k downstairs. Okay, everything for us is over k, but let's emphasize it here because I'll now pass to the generic points. Yeah, so I want to use that to define horizontal invariant for this map over this basis, right? Okay, so I take now a scheme, generic point. So my varieties are irreducible. There's one generic point. And we make a base change to that generic point. So like function field to the generic point is just a function field. Now on the other side, we get function field of the other guy. So that's a dominant map, and there's induced isomorphisms on it's birational map. There's induced isomorphism on the function fields induced by this sigma, and I also write it as sigma. Right, and then we have this x eta. I also write this as pi. So now it's a fiber of this. So it's yeah, it's a variety over this. And same here, same thing here. And I get a birational map here formally, just because it's map of fields, just considered slightly differently. Right, okay, and this is over k. So yeah, I assume these are regular now, so there's no problem in taking this fiber, generic fiber. But I'm literally now in this situation, in this Beer-Tilde situation, where I have two varieties over different fields. Everything commutes with projection to a smaller field. Okay, and as before, let's say n is dimension of x over f, so just dimension of x, and m is relative dimension of pi and pi prime. So yeah, so I define horizontal invariant of my original birational map phi as a restriction of scalars for this thing. I'm doing restriction of scalars for this thing introduced earlier. So this, yeah, sorry, maybe I'll write this phi eta, and this is phi eta. And now I have an element in the Burnside of this field, and I want to restrict it to this field. So from k beta prime, kb prime over k, restriction of scalars. So I'm kind of forgetting that I had a structure over this bigger field and treat this over k. I can sort of do either depending on the situation I want. So I either kind of keep track of them upstairs, but for the geometric applications, it's natural then to descend them to k and sort of say that we have some horizontal invariant over this field k. Yeah, I want to say where it lives. So it lives in where it should show Burnside of n plus m minus 1 of k. So previously, that guy was living in n minus 1, and then this restriction of scalars adds m because of this relative dimension m. So, like maybe let me try to make a picture for why these are horizontal invariants. So basically, the point, like separation I want to do is exceptional divisors on the two sides are of two types. Either they are seen on the generic point. So if I have some kind of fibration over the base, if this was my pi, then exceptional divisors can be kind of horizontal, so dominate the base and be seen at the generic point, or vertical, which don't survive at the generic point. When I pass to the generic point of these two fibrations, I only keep track of the ones which are seen at the generic point, and this means that they are horizontal, so they kind of leave over the base, as opposed to not dominating the base. So I can make this explicit by saying that, okay, explicitly, what this horizontal invariant computes is it's the sum as usual, like E minus D. E are exceptional for phi, and E exceptional for phi inverse, D exceptional for phi. But the point is that they dominate the bases. So if I look at this side, and then the divisors I look at here are the ones which dominate this base, so survive over the generic point of the base. So I want the closure of the image to be equal to the base. And same thing here. I want the closure of the image to be equal to the base. Yeah, so there's this kind of generic point of the base sort of logic that restricted to generic point, I only pick up those divisors which are seen from the generic point. Another way of saying this, seen on generic point, means dominating the base. So that's the claim made here. So you see here it's kind of not necessary. Like if you write it like in this language, then everything is already landing here. Yeah, there's like ambiguity where I want them to leave, but I want them to end up here. I don't have to twist by. Yep. Yes, so in a second we'll get rid of this assumption, but it's just easier to take generic point. If you think of, if you had a rational map, but still, yeah, there's a little bit confusing, right? If this was a rational dominant map, generic fiber is not super well defined. Okay, in a sec. You can take some open subset. Yeah, so in principle, indeed, what we could do, we could take the maximal open subset where this is defined and then do this. We'll do this in a second. But in principle, if I just have a rational dominant map, I have to explain what generic fiber means. It's not automatic. It depends on the choice of an open set where you are regular. So you have to be regular to do this. But depending on the open set, this thing will change a little bit. If you start removing horizontal divisors, your answer will change. It will be the same birational type, but it won't be a fixed variety. So yeah, we'll solve this problem. It's not a big problem, it's just a little technical issue that it's easier to do this first. Maybe I'll make an example. So that's getting a bit abstract. So I'll do an example when these things are trivial. So my example is conic bundles. I want to look at conic bundles. Conic bundles means, yeah, for me, this means now that they are flat and fibers are conics. Conics mean conics in P2, so this could be smooth conic, reducible conic, or unreduced conic. That's a natural concept in rational geometry, so conic bundle. Sometimes you want to relax it a little bit, but this is a natural thing, flat with this kind of condition. Right, so I want to know what are the horizontal invariants of this map. Maybe a question to the audience. Do people see what's the horizontal invariant of this map? Again? Almost. So let's see what we have to do. We have to look at the generic fibers. Generic fibers are conics. I have a birational map between conics, and it's an isomorphism. So let's see. So what I have to do is, by definition, I have to restrict to the generic points of the bases. This is a conic over some field, function field of the base. That's another conic. And the diagram will look like, okay, I have like one conic, another conic, and the birational map. But because they're curves, smooth curves, this is an isomorphism. So there's no exceptional divisors which are contracted either way. So in this dimension, there's no horizontal contribution, right? So, and it will be kind of important when we analyze different situations that, it's kind of obvious, I'm just saying that all the divisors will be vertical. All the exceptional divisors don't dominate the base because a rational map between smooth projective curves is an isomorphism. Yep. Yes, thanks. So maybe I want this to be generically smooth. Okay, so flat, generically smooth. So that I have some, indeed, if I am very unlucky and if my conics look like this, then something may go a bit wrong, because this kind of curves do admit birational maps, maybe, but smooth projective curves don't. Yes, that's right, yes. But typically, in these situations, we look at conic bundles. But indeed, if I had like elliptic fibration, it would be the same argument. Yeah, thank you. Yep. So you mean in the setting of fibrations? So, for example, if this was P4 or like some higher dimensional variety, even when they are isomorphic, the contribution can be non-zero. So it's a small dimension phenomenon that only for small dimensions we can hope to have things like this. Because definitely, if it's like there are like P4 on both sides, or P3 over funny fields like this, like then this can be non-zero contribution. Basically it's okay for curves and surfaces. And in higher dimension, this could be interesting and non-trivial. I mean, when fibers are curves and surfaces. Right, so I defined horizontal one, so the vertical one will be the opposite. But maybe before that, let's deal with this issue of, so more generally, let's look at rational projections. So let's look at this problem with the generic fiber. Yeah, maybe I'll stop saying this. So my horizontal maps are birational and my vertical maps are rational dominant always when I make these diagrams. Yeah, I want to pass to the generic fibers, but I have to be careful because I need to basically we can choose some loci where these are well-defined, so regular, and also we can choose the maximal one. That's the canonical choice. And it's important that here we can make a canonical choice. So I'm saying that U is X minus indeterminacy loci of locus of pi. So in other words, domain of definition of pi. And we've seen in this school that this is well-defined. It's the biggest set where, open set where this is a regular map. And the same thing for the other guy. Yeah, and then I end up with a diagram which looks like that. So I have now a regular projection. I can keep the same base. I still have a birational map because I passed the open sets. Nothing has changed here. Maybe I write it as phi u. Yeah, so I sort of traded this situation for this situation where I have regular maps, just by removing indeterminacy of the vertical guys. And then we define the horizontal for phi to be the horizontal for this phi u. So we make this canonical replacement and then track what are the horizontal divisors. Yeah, and the advantage now of this situation is that there's no problem in passing to the function field. And actually, function field here is kind of a little bit funny without doing this first. Okay, so now I have, in large generality, I have this horizontal invariant. And so we can now define the vertical invariant. So we set, so once this is defined, like this, we just said that the vertical is everything else. Okay? Explicitly, in a situation like this, so we can make this explicit. So explicitly, when pi and pi prime are regular, this vertical one is given by a sum as before. Yeah, so let's mark that equation. So we had this explicit expression of divisors dominating the base, but now we do the opposite. We don't dominate the base. With exceptional divisors D and E not dominating the bases. Yeah, so it's some kind of clear thing. So, for example, in this conic bundle situation, okay, so there's no horizontal ones, but there are definitely ones, could be ones which are exceptional and don't dominate the base. And now we take care of those. So, which land in some divisor in the base. So it follows from the definitions that we have full additivity. So the additivity property is that if we have a composition of this square birational maps, so in most generality, these vertical ones, these vertical projections are also rational, and this is phi. This is psi, then all three of them are additive. So how do we know this? For the original one, we already know this. The original one just ignores the fibrations, and this is one of the things we know from before. For the horizontal ones, I explained this here in this situation. And then once we restrict to the field K, this tau is disappearing, and we literally get additivity. This was additivity over kind of this field, but now we have a smaller field, and we forget this field and pass to the smaller field, which means we get rid of this tau, and everything is descended. And then vertical one is the difference, so it's also additive, because it's the difference of two additive invariants in this sense. So horizontal part is a bit like, for this rational projection setting, it's a bit hard to say what vertical means. yeah, it's easier to first deal with the horizontal part. Because passing to generic point is the kind of a canonical operation. Like when you have a divisor which is, when you have something in the indeterminate locus of this projection, you have to decide if it's horizontal or vertical. And it may be a bit confusing, but indeed, maybe that's the quickest way to set them all up. So maybe, so I don't assume varieties to be normal even. So for example, it could be that these maps are not defined on divisors in principle. It's not super important, but when this map is not defined on divisor, one needs to like think a little bit what to do with the divisor, and this way we don't have to decide this. It's automatically assigned whether it's vertical or horizontal. But indeed, for regular maps, we could just define both of these sums at the same time and write the sum over dominating the base, the sum over not dominating the base, and that's it. Sometimes it's a bit more convenient to work with, like for MRC fibration, for example, naturally it's a rational map. Of course, one can always resolve it to make it a regular map. Of course, yes. And also we can always resolve singularities, make it like, make it regular. No, sorry, not always, but in characteristic zero, we can resolve no, maybe if I don't want it to be smooth. Okay, anyway, there are ways to make it regular, but if I want this general thing, this is the way to go. Yeah. Mm-hmm. So, do you, inverse of normalization? Uh-huh. Mm-hmm. Yeah. The inverse, yeah, like so the, yes. 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 No, it's a little bit confusing. Some of the, yeah, so this is all set up well, and then one needs to, some of the examples will be a bit confusing in deciding who is vertical, who is horizontal. So especially when this pi and pi prime are not regular. We can discuss later. Yeah, no. We won't lose very much assuming they're regular, but just it's a natural, nice framework to play with. Right, so we have this additivity. What else do we have? Basically, I'll explain some vanishing results. So there'll be kind of, it's sort of boring up to some extent. I'll explain like three situations where these are zero. So it'll be vanishing 1, 2, 3. So we've seen this kind of baby vanishing over there, and there'll be more vanishing like this. So one will be for the horizontal one as above, and two other for the vertical ones. And once we collect some vanishing results, we'll be able to compute some interesting things. For example, for MRC fibrations for threefolds. A bit later today, we'll use MRC fibrations for threefolds to show that for threefolds over closed field, the invariant is always zero. And for that, we'll have to use some of these vanishings. And there will be another application at the end of the talk today. So the first vanishing goes a little bit in the direction of Claudio's question about more general vanishing like that, so of the horizontal ones. Vanishing one. So the statements will be that for certain self-maps, the certain type of invariant is zero or like computable in an easy way. Yeah, and the assumption is as follows. So pi has relative dimension up to 2. So 2 is the interesting case. And phi is a birational map from pi to itself, so square birational map. And then the claim is that the horizontal contribution is 0. And now, compared to this, okay, one-dimensional case was that. Two-dimensional case is something non-trivial. And like, actually, what we need an assumption here, we want characteristic field of the field to be 0, and you'll see why. Yes. Yes. Yes, thanks. Yes. Generically smooth, yes. Thank you. Yeah, characteristic 0, yeah, I guess it's, yeah, for example, if x was smooth, maybe in characteristic 0, that's not even necessary. Because if x was smooth, it's generically smooth, by generic smoothness. And if x was not smooth, we can take resolution, and nothing changes. But in principle, yes, that's what we keep in mind. Okay, so it's a statement about surfaces, right? So generic, so okay, the main case is, so dimension 1 is easy, so we assume pi has relative dimension 2. So what I have is the following thing. So I want to pass the generic points in these 2 steps I explained earlier. So I get a surface now. And the surface is over a field, which is the function field of this. However, we get non-trivial, potentially non-trivial automorphism here, which is trivial over K. Right? So that's a setting to think about here. So if there was no such thing, we would say, okay, but that's a surface, and we're looking at, so this, okay, what's the notation? This is phi eta, and if you remember, horizontal part of phi was defined in terms of this phi eta. It was basically, I have to look at its own invariant over this field and do restriction of scalars. Right, so kind of, I need to know why this is 0, basically. And in the first lecture, I was explaining that the first vanishing for the invariant is for surfaces. But in there, they were over the same base field, and it was identity on the base field. So, and actually, to prove this vanishing, we not just use the result for surfaces, but we use the proof of that result. So in the first lecture, I very briefly said that to prove the vanishing for surfaces, we have to attach to every surface some kind of class in Burn 0 of the field it lives in. Right? So there's this kind of atom of the surface. And previously, what I was saying about this assignment, so this is constructed by Lin, myself, and Susanna Zimmermann. The property of this construction was that if you do a birational map over the field it lives in, then you get the invariant of this birational map only depends on the source and the target by this formula. You have to take atoms that you have here minus atoms that you had before. And this is why it was vanishing, because for self-maps, this is 0. This is what I briefly mentioned in the first lecture, that this is the proof for vanishing for surfaces over the same field. And now, to use this construction here, we need to claim one more property of this atom, is that when you look at your surface and you compose the base with some automorphism or isomorphism to another field. Now we kind of exit the realm of varieties over a field, or a fixed field, and just work with varieties over some field. And then there's a valid thing to do this composition, and to think of this as a variety through this. It's not the same variety anymore. It's a very subtle thing. It's the same scheme, but different variety. Yeah, but and this is my sigma S, so it's a composition of this, so this is like sigma pi kind of thing as a surface. Yes, and the claim is that it's equal to sigma times sigma applied to M of S. So M of S was living in this thing, and we can apply automorphisms to these things, and this is a valid thing to do. And this is something which is true by construction. I didn't explain the construction in full detail, or in any detail, but this is something one can check about this zero-dimensional class attached to the surface. And then basically, in this situation, we do the following thing. We compute C of phi eta. We can consider this birational map as a map between this surface and this surface, but now over this field. So I have to write the target. So I'm using this claim. I'm writing the target class minus the class of the source, which is sigma S. Right? And by this formula, it's M minus sigma ms. But now I restrict the scalar. So it doesn't look like zero. At this point, it doesn't have to be zero, because they were different surfaces over the field. However, if I do the restriction of scalars, so the horizontal part is the restriction of scalars, it's zero because of this diagram. If I first do sigma, and then the restriction of scalars is the same as I do restriction of scalars straight away. It's the same thing after we pass to this smaller field. Yeah, and this is how it works. So from this perspective, fibrations between maps between Delpezzo fibrations, for example, also have vanishing horizontal part. So this was vanishing for the horizontal part, and in principle, that's all the general result like this we can claim, because we know that for threefolds, for fields like this, it doesn't have to vanish. There was this P3 example yesterday, P3 over a function field of P1, where this is non-zero. So that's all we can hope for. The other two vanishing results are about vertical invariants now. So there's vanishing 2. I have a morphism like this, and I'm looking at a specific type of birational map, so over the base. So as I said, in general, this is smaller. So these are triangle birational maps acting trivially on the base. In other words, I have yeah, and then the claim is easy. The vertical part of this guy is 0, right? So it's specific to this horizontal and vertical things, because previously there could be no such result when there's no base, because if this is a point, everything is horizontal. So it's kind of literally like, this way, by splitting them into horizontal and vertical, we earn some vanishings we can use. So the proof is kind of silly. We just remove all the vertical divisors from the base, and we get 0. So let's see. So we set, consider an open set now in the base. Let's call it V. Where I remove everything I don't want to have in my base. Specifically, there's a union of phi d, which are exceptional for phi, and not dominating the base. So I just remove all the, okay, you'll see, I just remove all the vertical divisors I can. So, and then pi of E, where E is exceptional for phi inverse, again, not dominating the base. Right, so I say, just remove downstairs everything we don't want to have. So, like, what's the point? The point is that if we restrict, we have no vertical divisors anymore. So we can think of this kind of diagram. So I had X over B, X over B. This was identity. And then I have this V here, and I restrict to XV. I take the base change to this open subset. And I do the same thing on this side. So I want to trade my map for a better map. This was phi, and I can call it I and I. And this whole composition, we can call phi V. So the point is, visibly, the vertical part of phi V is trivial because we have already removed all the vertical divisors. Right? So we were allowed to remove them, and now there's none of them. Horizontal ones may still be there. That's one thing. And another thing, there's a standard kind of thing which is very useful. If you have a conjugate map, their outputs are the same. Specifically, you can relate phi and phi V by conjugation with this I. So there's an I inverse going this way, bit funny birational map, I inverse. And what we can write is that phi is, you can go here, and then back. All of these are birational isomorphisms, so we can invert them as we want. So I, phi V, I inverse. Yeah, and then, so it's a kind of a standard argument here that you end up with C of I, C of phi V, minus C of I, and this is 0, and this cancel each other, so this whole thing is 0. Yeah, so kind of as I'm saying, conjugation on the map doesn't change the output. If you manage to conjugate to something with, I mean C vertical. So why were we allowed to do this? Yeah, this finishes this little proof. Because they were fixing the base. If they were changing the base, we couldn't, if this map was of infinite order, for example, and we would try to remove all these contributions, there's no such open set, basically, right? Because we have to look at all iterates, and we cannot just remove them. They may still be there. But if it's the same base, we can remove them, and that's it. So even then, there may be some problems, even as automorphism. because somehow you may want to iterate. If it's finite order on the base, then it's easier. If it's infinite order on the base, it may be difficult. Okay, there will be third vanishing now, and for that I have to set up a new definition. So the third vanishing is slightly more subtle. It applies to special types of fibrations. So I say this is birationally trivial. So it's a homemade definition for the purposes which will be here later. In codimension 1 with fiber F, sorry, maybe with fiber T, if for almost all divisors in the base, prime divisors P in the base, when we restrict to this divisor, we get something trivial. So this means we have so I'm making a base change to the function field of this divisor. I'm looking at what happens generically on this divisor. And I want this to be birational over this field to my fiber. So I want the map sort of to be like, have the same stuff hanging everywhere. But maybe I don't control the generic point of the base, but at least I want to control all the divisors on the base. And we'll see an example and how that's relevant. So the silly example, the easy example, is when my map is just trivial or locally trivial. For example, if I have projective bundle, so the risky locally trivial projective bundle, pi m fibration, then it's true. So pi is that. So birational trivial in codimension 1 with fiber pi m. So maybe there was some global structure. Maybe there was like vector bundles and projective bundles, but over generic point you still get a trivial projective bundle, and that's it. In this case, it was even better. So even at the generic point of the base, still it's true. Yeah, and I forgot to say, so with algebraic geometry, so almost all means all except finitely many. So all except finitely many prime divisors have this property. Maybe there could be some singularities over finitely many divisors. So the more interesting example, and kind of why this definition is useful, is you look at conic bundles. So you look at the following situation. So algebraically closed field, and then a very specific type of conic bundle. So threefold conic bundle. So what I mean is dimension of X is 3, and B is a surface base of the conic bundle. Right? So conic bundles don't have to be Zariski locally trivial. There's some kind of conic hanging over the generic point which may have no rational points. It's a question of sections. If you are lucky to have a section or rational section, then it will be a bit like this. If you have no rational section, that's really like a conic bundle. It's not Zariski locally trivial, only étale locally trivial over some open subset. Yes, but still I claim that in this situation, it's also true. So pi is birationally trivial in codimension 1. With fiber P1. What I'm saying, if you take a general curve downstairs, and you restrict your fibration to this curve. So that's now a ruled surface. So like this is surface over the curve, which is a conic bundle, and actually Zen's theorem says that over curves over algebraically closed fields, these guys now are all split, so there is a section, rational section. Yes. Yes, general curve, yes. So there will be some curves where fibers are singular, yeah, everywhere singular, yes. Reducible or non-reduced, or maybe, yes, maybe even non-flat, right? But okay, I assume maybe flat. But anyway, yes, general curve where the fibers are smooth, so that I get generically smooth conic bundle here, and then by kind of theory of surfaces over k bar, that's literally a ruled surface. So that's birational to C times P1. Yep. And if it wasn't a closed field, such non-split things would exist, but not under this assumption. Okay, so vanishing 3 is the following result, which actually is a bit more general than vanishing. So we work with those guys. So pi, I assume pi is flat, and generically trivial, sorry, how do I call it, birationally trivial in codimension 1. And I take phi from a square birational self-map of this. So what's the picture? The picture is that I have some interesting map induced on the base. And the claim is that the vertical invariant can be computed as follows. So it's not quite zero, but it's controlled by this thing downstairs. So for example, what we've seen, if this was identity, then without any more assumptions, it's zero. In general, you have to do the following. You have to look at the invariant on this base variety and multiply by the class of the fiber. So in other words, how do you know what you have added or removed upstairs? You have to check what you have added or removed downstairs, and then multiply by the generic fiber. So, for example, if this is an automorphism, regular automorphism, then of course this is zero. And that's how it's like a vanishing result. But even when it's automorphism without this assumption, I'm not sure that this is zero. This is an assumption needed to make this work. So yeah, maybe I won't be proving this. So basically, to prove this, you have to kind of resolve the map by two regular maps with a normal base here, and then carefully see what you have removed, what you have added. And somehow the point is that we are checking the vertical contributions, and if we look at each of these guys, vertical divisors almost all look like a product of the base divisor with a fixed fiber. Sorry, I had a T. Yes, Yes, thanks. I didn't want to call it F because F was a field before. So T is the fiber, yeah, thanks. So almost all vertical divisors have the form divisor times T, and I have to see what is added and removed, and this kind of infinite sum will boil down to contribution from the base. Yeah, but maybe no proof now. So maybe in the last 10 minutes, I'll use this to finish the proof of a theorem from yesterday. So yesterday was this theorem A, which was saying that if X over C is a threefold, any threefold, then the Motivic invariants of birational self-maps are trivial. And we did check the rationally connected case. And now I explain how we can check the other cases and what the other cases are. So yesterday, we used intermediate Jacobian to prove to give a proof when X is rationally connected. And the other cases are a bit different. So, but they use this kind of technology. Okay, so what do we do? So we look at MRC fibration. So this morning I started with recalling that any variety has so-called MRC fibration, maximally rationally connected fibration, where the base has very few rational curves, not uniruled, not covered by rational curves, and general fibers are rationally connected. And so sort of all varieties split into categories according to this MRC fibration, and Harris calls the relative dimension of this rational dimension, or rationally connected dimension. So this is relative dimension of pi, kind of maybe rationally connected dimension. Just kind of, you have variety of some dimension, maybe n, and this can take values from 0 to n, and the complexity moves in between this. So we have threefold, so we'll have 4 cases to look at, depending on this rational dimension. So we have to kind of put all the vanishings together. It will be like the, will be different sort of arguments in each case. Okay, so rationally connected dimension 3 is done. So X is rationally connected, and we have checked this. Rationally connected dimension 2. So what this means is that we have yeah, right. So, okay, so I kind of earlier insisted on rational maps, but I also said that if we want to, we can resolve these maps and make them regular, and maybe it's convenient to resolve them and work with regular maps. So, so basically at this point, I can replace X by any birational representative. In particular, I can assume, and this is what I'll be doing in the proof, that X is a smooth projective threefold, and that B is also smooth and projective. Yeah, so we are over C, so we can definitely resolve all the singularities we want. Right, okay, so the point is that B is a curve here. B is a smooth projective curve. And therefore, what we end up with is an isomorphism here. And I have to explain separately the horizontal and vertical vanishings for this map phi. Yeah, and what I call vanishing 1. So like relative dimension 2 fibrations, self-maps, implies that the horizontal contribution here is 0. Yeah, because these fibers are surfaces, therefore nothing will happen on the generic fibers. And yeah, so for the vertical contribution, it's some kind of similar logic to this vanishing 3, but one needs to do a little computation. Yeah, basically, like, so we want to know how fibers are changing from here to here, and to show that they don't change, and in spite of this automorphism of the base field. Yeah, and maybe I'll just put here 0 is like an exercise / simple computation. Yes. So, yeah, like genus of this curve is positive because of this is a base of MRC fibration, supposed to be non-uniruled curve, and so it's not P1. And then, like, if it's genus 2 and higher, it's a finite order automorphism, and we can play with this. In genus 1 case, it can be infinite order, and it's more interesting case, indeed. So what's the next case? Next case is rationally connected dimension 1. Now the roles of the fibers and the base are reversed. So I have this situation where my base is like non-uniruled surface. And for surfaces, non-uniruled is the same as non-ruled for surfaces over algebraic closed field. Yeah, so kind of surface without many rational curves. And yes, and who is the fiber? The fiber is rationally connected. And so, in fact, one can make further modification and make this pi into a flat conic bundle. And that's actually using a theorem of Sarkisov, who is known for links, but actually what he proved was models of conic bundles. So such one-dimensional fibrations, where generic fiber is a rational curve, can be made into flat conic bundles. So again, like horizontal invariants are 0. Either you say just because the fibers are curves. Yes, and for the vertical part, we're using what I call vanishing 3, because the main example for this concept of birational trivial convention 1, which wasn't like obvious, was this setting, the conic bundle over a surface, right? So the point is that pi is birationally trivial in codimension 1. So we can apply vanishing 3. Okay, one more thing I need to claim here is that this is an isomorphism, actually. This is a regular automorphism. And, okay, what's the reason here? The reason here is these are KNF surfaces. You can replace, in these birational types, like non-ruled will mean you have a KNF model. So KNF, you can replace it by KNF surface, and then such surfaces, all the birational automorphisms are actually regular. Yes, we're kind of using every little detail we can squeeze out of the situation. Right, and then we can use that I have to do C of sigma times P1, but this is 0 because I have an automorphism downstairs. If it wasn't automorphism, maybe I wouldn't know what's the result. So what's interesting kind of in this proof is that while it's clear that P3 or rationally connected varieties should have more birational maps and should be more things to check, the proof for the other guys is kind of different. So we don't use that. We have already checked it for P3. It's kind of irrelevant that for P3 it vanishes. It's a different sort of proof. Yeah, the final case is easy. It's rationally connected dimension 0. So X non-uniruled. So basically X equals B. X non-uniruled, right? And again, we can replace it by using MMP by KNF. This is some kind of MMP result. And in this case, then every birational self-maps, not here I said it's an automorphism, but it was because we're in dimension 2, is what's called pseudo-automorphism, which means has no exceptional divisors. Yes, and hence E of this phi is 0. Right? Yeah. So X won't be smooth, you're saying. Yes, okay. Yeah, but I suppose this should still hold, right? Yeah, thanks. Okay, so this finishes the proof of this theorem. They are different for cases, and the next lecture tomorrow I'll use this horizontal and vertical invariance to do some non-vanishing. So today we see a lot of vanishing results, and tomorrow I'll concentrate on how to use this to construct interesting example of non-vanishing for the invariance. And that's it. Thank you. Yeah, it's like, you mean when it's like a conic bundle over n minus one dimensional base, which is not uniruled, this kind of thing. So 0, yes, and 1 and 2 are kind of a little bit problematic. So I think, unfortunately, these two intermediate cases are not generalizable in the sense that we used both at the base and the fiber are small dimension somehow. Like in So, for example, like one thing which was used here is that conic bundles restrict trivially to divisors, and this is specific when the base is small dimension. If this base gets one more dimension, we won't be able to check this vanishing here. So this is how we're using not just the fact that it's rational connect dimension 1, but also that the base is 2-dimensional, unfortunately. So one cannot quite generalize this, and similarly, one cannot quite generalize this because here we're using that this is a surface and that's the curve somehow. So, and it looks like as soon as you weaken at least one of them, there will be non-vanishing of some kind. Yeah, thank you. Mm-hmm. Like these types, different types, but over small fields. Yeah, so even for real numbers, where I think, yeah, this may be okay for real numbers, but these other cases for smaller fields, I'm not so sure, because here we used both, at certain times we used both characteristic 0 and algebraically closed. So, for example, this thing about conic bundles being trivial sense theorem was using algebraically closed here, and yeah, so I'm not sure. So the feeling is that for this intermediate types, they should vanish more easily, but the argument I have at the moment applies only to algebraically closed fields. Yeah, thank you. Yeah. There's a question. Yeah. Mm-hmm. Yes, that's right. So this I wasn't maybe very clear about this. This is functorial and canonical. If you have isomorphism or like birational map between X and another guy, and you look at rationally MRC fibrations on the two sides, you get a square birational map. In particular, dimensions of these fibers is the same, right? Like, so you have birational map, it induces one here, and it kind of preserves the fibrations. Yeah, intrinsically, it measures like, sort of the chunks of your variety, which are covered by rational curves and cover everything. Yes, there's maybe some kind of intrinsic meaning to this, but the point is that it's functorial. So there's just one. It's a well-defined thing birationally.